Good afternoon, everyone. Thank you for joining us for today's seminars about the neutron quantum computer. For who does not know me, I'm Dongyu Kim, and I'm an assistant professor at KAIST Physics. And it's my great pleasure to have Dr. Tommaso Macrì and Mino Kwon from QuEra Computing. QuEra Computing is the quantum computing startup located in Boston. It is spun off from the MIT Harvard research on the neutron quantum processors, and the QuEra Computing is developing a full stack quantum computers from the neutron quantum processor to all the way up to the user interface now, which is accessible throughout the cloud service via the Amazon Web Service. And Dr. Tommaso Macrì is the senior research scientist at QuEra Computing. And before joining QuEra, he was a professor in the Department of Physics at UFRN in Brazil. And before joining QuEra Computing, he spent his sabbatical at Harvard. And he will tell us today more about the quantum computers. The title today is the dual mode quantum computers. Before we start, if you have any questions, please interrupt during the talk. And with that, please take it away. I look forward to hear your talk today.
So good morning, everyone. First of all, thank you, Dongyu, for the very kind introduction and for hosting me and Minho today here at KAIST. We are very happy to be here. We have spent almost 1 week in South Korea already, joining the event Quantum Korea that took place in Seoul over the past 4 days. So again, my name is Tommaso Macrì. I'm a senior research scientist at QuEra Computing, and today I would like to highlight some recent activities that we have been doing at QuEra. Again, feel free to ask questions either during the talk or at the end, or please feel free to reach out to me by basically shooting an email to my address. So QuEra Computing, the mission of QuEra is to build quantum computers based on neutral atom technology. We have a dual mode 256 qubit machine, which is called Aquila. Aquila means eagle in English, and is publicly accessible on Amazon Bracket. By now, really tens of organizations are using our quantum computer regularly on the cloud, and we are focused to deliver a real life value at every stage, from the point of view of the technological development of our machines up to the algorithmic level. And finally, one of the big goals of QuEra is really to develop a noise resilient and scalable quantum computer. We are very much attached to our scientific foundations, to two really outstanding institutions, such as Harvard and MIT. Our 4 founders, Misha Lukin and Marcus Greiner, are from Harvard, as well as Alex and Nate, who are alumni at the same institution. Vladan and Dirk are professors at the MIT. QuEra was born in 2019 as a spin-off of these 2 academic institutions, and our big product, a big splash, was made back in November 2022, so already 8 months ago, by launching our platform on Amazon Bracket or AWS Bracket. During this time, we basically very closely followed the scientific breakthroughs made both at Harvard and MIT in terms of applications to, for example, quantum simulation and optimization, as well as for what concerns the development of high-fidelity quantum gates, which are essentially operations that can be made on top of qubits, both in terms of single qubit gates, as well as this recently announced high-fidelity 2-qubit gates with 99.5% fidelity. QuEra, as a quantum company, is what is defined a full-stack quantum company, in the sense that it develops the hardware, again, the machine that you've seen in the previous picture, which is called Aquila. Then we also develop our own software, which is called Blockade, that you can easily and for free download from GitHub. It's Blockade with a Q here. Blockade, you can use Blockade basically both as a simulator or an emulator, especially for relatively small quantum systems, but also as what is called, technically speaking, an SDK, which means that you can prepare your jobs, you can create your own notebook to do some emulation or really simulation of your quantum system, and then launch your quantum simulation directly on Aquila, our machine, through Amazon Braket. And finally, on top of these two layers, hardware and software, we develop applications, algorithms and applications that are, of course, very much targeted to the hardware that we are currently developing. And we also basically want for these algorithms to be useful, and that's why we also partner with very high-level, very relevant companies and corporations to provide, again, real-life value for potential use cases of interest. Another thing, of course, as you can see here, this is an example of what I will show later of a quantum spin liquid. So we are also very keen on collaborating with very strong academic institutions to make sure that we basically cover the whole spectrum of applications from academic to business use cases. I just wanted to advertise just a quick more thing about our emulator, Blockade. In particular, Blockade is written in Julia, for those of you that are very interested in perhaps in programming, coding, which is a very, very important, very relevant for for very high performance. But it is also relevant for the possibility of deploying Blockade on clusters, in the sense that it supports both GPU acceleration as well as multi-threading. I would be happy to discuss more details perhaps after the presentations for those of you that are interested in knowing a little bit more. Let me now dig really still superficially, but a little bit more into the details of how our technology actually works. So how does a neutral atom quantum computer work? Well, there are a few fundamental ingredients. The first one, of course, we are talking about neutral atoms. The basic ingredient is an atom. In particular, in our platform, we use rubidium-87 atoms, which are here sketched or represented by this purple sphere. These atoms can be trapped by tightly focused laser fields stochastically. These laser fields are called optical tweezers. And then once we trap those atoms, we can control, and of course we can image those atoms. This is just a snapshot of an atom trapped by a laser field. We can control the internal degrees of freedoms of the atom. In particular, we focus on, for the implementation that I will be talking about in the next few minutes, on two specific levels that we can encode, on which we can encode the two qubit basis states. In particular, they are called, I label them as G, like ground, for ground state, and R, that is an excited Rydberg state, which means a state with a very high principal quantum number. Now, given these two states, we can control the dynamics of the quantum dynamics of excitation between these two internal states by an external field, by an external laser, whose strength is proportional to this parameter called omega, or Rabi frequency. Now, all these mechanisms, of course, can be extended to more than one atom. In particular, we can focus on two atoms. Again, this is a snapshot of a second atom here. And now the question is, if I want to really understand and develop some non-trivial physics or non-trivial application on top of this system, I really need to start preparing quantum correlated states or entangled states. Now, what is the key to developing this type of, or creating this type of states? Well, one possibility is to exploit interactions between these Rydberg atoms. However, this interaction is position dependent. In particular, it decays as a power law, 1 over R to the 6. This is a particular example of what is called a van der Waals interaction. And therefore, if you put the atoms too far apart, the interaction decays so quickly that basically the atoms do not see each other at large distances. Here, by large distances, I mean distances of the order of 10 microns or more. However, and therefore, what's the implication of this? Well, if you start from the physical implication is that if you start from the ground state, so if you initialize your register with the two atoms in the ground state, you can essentially simultaneously induce Rabi oscillations between the ground into the excited state for both atoms, because essentially they do not talk to each other. However, if the atoms are now close by, and in particular within distances of few microns, then what happens is that the interaction here is so strong for such distances that basically we will inhibit the simultaneous excitation of both atoms into the Rydberg state. So what's the consequences of that? Well, if you start from both atoms again in the ground state, the only possibility is to excite a coherent superposition of the two atoms into just one Rydberg state. Now, in the case of two atoms, this is just an instance of what in quantum information is called a Bell state. But if you extend the system to n atoms, where n is larger than 2, the coherent superposition of a single excited state is what is called a W state. Now, this mechanism of exploiting interactions to induce or to create entangled states in the context of neutral atom simulators is called a Rydberg blockade. And here, that's why we use this nomenclature here. So again, three main building blocks: atoms, lasers, in particular trapping lasers such as optical tweezers, and finally Rydberg blockade to induce non-trivial interactions. The other thing that I want to mention is that, again, we can scale the system up from 1 to 2 to n atoms. Now, the conditions that we get in order to understand the non-trivial dynamics rising from this relatively complex system, set of two-level systems, is given by this Hamiltonian. So I will not provide too many details, but let me just very briefly comment on the three terms that we see here. So we spoke about van der Waals interactions, or long-range interactions. And the term that is responsible for such interactions is the last one, proportional to the parameter, to the interaction strength Vij, again, position dependent, multiplied by two operators, Ni and Nj, that essentially count the number of excitations in each side. So this term basically is different from 0 only if Ni and Nj are both 1. If one of the two or both are 0, then this term essentially vanishes. Please.
So in the first term, what is the state one?
Yeah, let me just comment on the first term in a second. I was just focusing on the third. So the second term here, proportional to this coefficient delta, the detuning, which can be position dependent, is a term called, again, acts as a sort of chemical potential for the system. Here I'm using a sort of parallelism between statistical mechanics and AMO physics. And what you see here is that when delta is positive and Vij is again positive, the two terms compete. So again, if you increase delta, if you increase the detuning, what happens is that you will start populating the system with Rydberg excitations. Now, let me go to the first term that our colleague was asking about. Here, actually, 1 stands for 0 and R stands for 1. Or if you want, 1 stands for ground and R stands for Rydberg. This term here is essentially the non-commuting term with the other two terms. And that's what essentially enables true quantum dynamics for this type of system. In particular, it's a spin flipping term in the sense that if you start from 0 or if you start from ground, you excite to Rydberg and vice versa. And here, the other important point to consider is that we can individually control the strength of the detuning, the amplitude, or basically the strength of the Rabi frequency, as well as its own phase. From the perspective of quant math or statistical physics, this model can be easily rewritten in terms of a very well-known model in statistical physics, which is called the Ising model, in the presence of a transverse field, again, proportional to this detuning omega, to this Rabi frequency omega, and a longitudinal field proportional to this term called the detuning. So again, we can sort of span or across the whole spectrum of applications in physics from, let's say, AMO physics based on the intrinsic model or intrinsic mapping to Rydberg states, statistical physics on condensed matter when we actually talk about the many-body physics generated by these non-trivial Hamiltonians. So how does this quantum dynamics then is enabled? Well, we initialize our register, so our sets of qubits usually all in the ground state 0, and then we run this time-dependent Hamiltonian. So we run the dynamics by basically changing the or varying in time the pulses of given by the detuning omega and potentially their phase. The other important feature is that we have certain flexibility in designing those pulses. Here, what I'm showing is a set of rectangular pulses that can be, for example, useful to generate highly non-trivial non-adiabatic dynamics that can be relevant for applications such as QAOA, for example. But we can also use more regular Gaussian pulses that can be instead applied, for example, to study annealing or quasi-adiabatic type of dynamics. Or we can really be creative and using these sort of fuzzy pulses, perhaps to study very highly non-trivial type of dynamics. The other important ingredient for such platforms is the fact that we have a very large tunability or flexibility in designing the geometry of our setup. So, for example, what I'm showing here is an instance of a square lattice with hundreds of qubits. As I would like to just quickly recall that we can, the service that we provide through Amazon Bracket allows you to work with up to 256 qubits. Again, we can be a little bit more creative and, for example, form a Kagome lattice, which can be generated by hexagons and triangles, or even a map of the world here, very schematic. Again, no regular geometry. Just a second. And finally, we can even print our first hello world with our neutral atom quantum computer. I see that there is a question. Yeah. The x-axis, of course, is the time. Here there are no axes, so you see it's it's very schematic. So let me make a brief comment. So on the x-axis we have time, and typically the time scales are of the order of a few microseconds. On the y-axis we have the amplitude of these parameters, omega, delta, and potentially the phase. So you can change in principle the three of them. Of course, in the service that we provide, there are some constraints in the amplitude, in the values of the detuning, the Rabi frequency, etc. The model that I described until now is what we would call generically analog mode or analog quantum computing, in the sense that the dynamics that we apply on top of our initial register, of our register of qubits, is basically induced by a continuous time dynamics. So we define the pulses that we have seen in the previous slide, and then we run our dynamics essentially in a continuous way. On top of that, we can, of course, again, play with the geometry and define all these nice type of patterns. This type of mode, called the analog mode, is complementary to a, to a different type of mode to realize quantum computing, which is the so-called digital or gate-based mode, which is a universal way of performing quantum computing algorithms that is based instead on the discretization of the dynamics on top of our initial set of qubits. So here, what we do is basically to start from we initialize our system again in the state where all the atoms populate the zero state. And then we apply sequences of gates or layers of gates, where in each layer we essentially produce a number of, or we realize a number of gates, which are quantum operations on top of those qubits. And they can be either single qubit, 2-qubit gates, or multi-qubit gates. Now, from the physical standpoint, it is also interesting for you to consider the fact that while, whereas here in the analog mode, we typically implement or map our basis states for our qubit into the ground and the Rydberg state, to enable the digital mode, instead, we want to map the basis state for the qubits into very long-lived or long coherent states, long-lived or states with long coherence time, such as hyperfine states. Once we employ these two hyperfine states to enable interactions and therefore the possibility of having non-trivial two-qubit gates or multi-qubit gates, we excite one of the two states into the Rydberg state. And therefore, by having two atoms that are still sufficiently close by, but where we encode these qubit states into the hyperfine state, the only way for them to interact will be to essentially have a three-level system instead of a two-level system as before, such that when they are populating both the Rydberg state, will create some non-trivial entangled dynamics. Let me briefly comment on potential applications of these neutral atom setups to potential use cases. So I would like to classify the type of use cases in terms of three different categories. The first one is what we call machine learning for both classification and regression and prediction. And in particular, I will just flash on a method that we are currently developing, which is based on quantum reservoir learning or quantum reservoir computing. The second class of problems are called optimization or quantum optimization problems to solve certain combinatorial problems that are very much present in classical optimization, and then essentially try to encode them within our neutral atom arrays and to run some non-trivial dynamics to find out what is the solution of or the maximum or the minimum value of certain cost functions arising from the definition of those problems. Let me also comment that there are some native problems that we can solve within the optimization space, and these are the so-called maximum independent set problems. I will say just a couple of words in a few minutes. And then, but we are also able, by using some sort of overhead, which means by using additional qubits to encode all the variables of our optimization problems, to solve more complicated or more general problems, such as Kubo problems, for example. The third class or third category of problems that we can solve with these neutral atoms is called quantum simulation or analog Hamiltonian simulation, if we are doing this type of quantum simulation within the analog mode, or digital quantum simulation, again, if we use the digital mode. The idea here could be, for example, to study or to investigate problems that are inspired by the investigation of equilibrium or non-equilibrium phases of matter in the context of QuantMat, for example, or more fundamental theories of physics, such as lattice gauge theories. Again, we are very much inspired here by academics like you, and this is precisely the type of use cases that many of you might have encountered during your early stage career. Let me comment briefly, please.
Can I get more the explanation of what is the Kubo is?
Yeah, Kubo means quadratic unconstrained binary optimization. If you want, again, we can discuss a little bit later after I speak about maximum independent sets, or perhaps after the talk if you want. So let me briefly sketch on machine learning. Typically, classical neural networks rely on the fact that we need to train billions of parameters, and this training is hard due to the fact that you need to update the weights of the internal layers of our neural networks. This is particularly challenging if you want to extend this type of techniques to the quantum realm, because for quantum type of machine learning applications, not only do you need to basically do this technique or apply this method called backpropagation to update the weights, but you also need to collect the statistics of all measurements to make sure that you are able to do the right type of backpropagation or update of the weights. Now, there is a way potentially that we are currently starting to explore, which is based on a technique called reservoir computing, where we basically replace the internal layers of this neural network by what is called a reservoir. Now, the word or the term reservoir here is actually quite general in the sense that the whole idea here is to produce some complex dynamics that can be generated, for example, by a classical spin system, or even by a bucket of water, where you monitor, for example, the amplitude of the oscillations of the waves on top of the water. Then once you do this type of measurements on the reservoir, you apply just some linear regression on the output, and then you will find out whether you will be able to do precise classification or regression of certain algorithms. The type, this reservoir computing, classical is very well known, and for example, is used in the context of weather forecasting. The thing that we actually want to try to implement here in the context of neutral atoms or neutral atom arrays is the quantum version. And when I say quantum, I actually mean by the replacement of the classical reservoir that we have seen in the previous slide by an atomic array, where, for example, we start by our initial image. Suppose that we want to do classification. We start with an image of a horse or a boat or a house, etc. We do some downsampling, some principal component analysis, for example, and then we do the encoding of the relevant degrees of freedom, either on the detunings, again, these parameters, which can be locally controlled, or into the positions of the atoms. The positions of the atoms are actually very relevant because, as I mentioned before, the interaction between the particles is position dependent. So if you change the position of the atoms, eventually it will change intrinsically the dynamics of the system. Now, once we do this encoding, we can run some quantum dynamics enabled by the Hamiltonian that I was showing before. Eventually, we do some measurements and compute expectation values of the number of excitations or their correlators, and I and J at different positions. And finally, we apply classical linear regression, which is, again, very efficient as a technique and very fast. And finally, obtain our label for the original image. So in this case, the output is a horse, which is exact. I think it is the correct one, right? It's not a boat or something else. Now, let me show you some results. We applied this technique to the case of, to a very well-known data set, which is called the MNIST data set, which is a multi-digit classification problem, where we basically need to detect whether the prediction of these handwritten digits are correct or not. So in this case, the prediction is 1, which is, I guess, the right prediction here. But in other cases, for example, here it is clearly a 9, but the prediction is wrong because it says it is 7. So what are the results that we got after applying this quantum reservoir learning to this particular problem? Well, we see the results here on the right. And in particular, I want to comment on the fact that if we apply the full quantum version of this algorithm, we obtain accuracies which are actually compatible with other state-of-the-art techniques, such as KNN, kernel support vector machines, or a 4-layer neural networks, for example. There is an interesting observation here to be made by observing that if we remove the effect of quantum correlations by basically placing the atoms sufficiently far apart, such that, again, the atoms do not see each other, the dynamics, I would say, is still intrinsically quantum, but there are no useful correlations, and the absence of useful correlations translates into the fact that there is a relatively high error in the prediction of the correct digits from the MNIST dataset. Again, quantum is better than quantum without any type of interaction. The second kind of application here that I would like to very briefly sketch in the simplest possible example. Please.
So what's the problem that you're going to solve with this systems? You mentioned that if we increase the number of the dimensions or the number of weight that we have to update, then if you use the classical systems, the problem is the gradient is vanishing. So is that the case that we want to use neutral atom? So what kind of problem they're going to solve with this the quantum the neural network?
In the case of neural networks, the problem is that you have usually a lot of internal layers. You have a lot of parameters, and then you need to update the parameters to be able to extract a useful prediction. In the case of the reservoir computing, both classical and quantum, you don't need this training of the reservoir. You do just a simple linear regression at the very end. So you still need to extract the statistics in the quantum case. That's of course crucial because the measurement in quantum mechanics is probabilistic. So you want to extract useful information by the expectation values. But once you do that, you can basically forget about your quantum dynamics because you got the results and now you train your single layer neural network and obtain the result for a classification or a regression problem. So you basically bypass all the problem of updating the neural network weights that you would have in standard multi-layer classical neural networks, for example. Does this answer this?
So the result that entanglement helps to reduce the error rate. You commented.
I would love to elaborate more on that, but this is again one sort of. So what I can say, it's sort of a heuristic, so it's not really provable in this context. So suppose that you have many atoms which are very far apart. The only thing that you would gain by placing these atoms very far apart is to have basically a much faster collection of the statistics. Because if they don't talk to each other, essentially, basically, there is no real value in using this technique or in using, for example, one single atom compared to 200. Instead, in the case of quantum, the fact that you have more possibilities of generating non-classical states or non-trivial quantum states apparently enables or is actually the key to the better performance of the whole algorithm. What do I mean? I mean that the only way to really exploit the fact that you have many atoms is by placing them closer enough. If you put them very far, very far apart, I mean, intuitively, what I would say is that basically you are just sampling better or measuring much faster your system with respect to just a single atom. But at the end of the day, it will be just, again, as having a single quantum spin for your many-body system. I don't know if this, but we can discuss perhaps later. Please.
I understand that this slide has been generated random numbers or different data. Am I right?
So you start from there. That's sort of the encoding part. You need to do the encoding. Encoding means either you tune the parameter of the intrinsic parameter of your Hamiltonian, which is the tuning, for example, or you tune the position of the atoms, which eventually end up being parameters of the Hamiltonian because they change the weights of the interaction term Vij. But once you define the encoding, you need to run the dynamics and take the measurements. Right. So there is a dynamics. Because from the dynamics, we extract some measurements on the number of excitations, and then by monitoring those excitations, we are able to extract or to run a certain classical linear regression on top of those results. So in general, you want to have some certain control on the position or the tunings. Now, it is a fact, and that's where the interest toward this type of methods arose both in the classical as well as the quantum case, is that it looks like that the system, the method is robust enough by basically changing or tuning or displacing, for example, a little bit the position of each atom. So the method should be robust enough. It should not be fine-tuned. Otherwise, we would go back to the problem of really training or overfitting of a certain neural network. That is something that is very well known in the classical case. So again, what I'm saying is sort of preliminary in the sense that there are some theoretical and few analytical results on this. I can also give you the reference. And there is a paper from last year. But still, these methods need to be studied a lot. I mean, I would say, to be able to make sure that they are widely applicable to a very large number of potential use cases. What we have shown here is an example with the MNIST database. We were now extending the number of databases to make sure that, again, the usefulness is sufficiently wide. But if you're interested, we can discuss later. Let me very briefly speak about optimization. You tell me if I'm running out of time.
Right.
It's okay for now?
Yeah, it's okay. Yeah,
It's okay.
cool.
So again, combinatorial optimization, the goal is to maximize the objective function over, in general, an exponentially larger space of possibilities. An example of that is the so-called maximum independent set, whose goal is to find the largest subset of vertices such that none of them are adjacent. Let me make a very concrete example by considering, for example, potential locations of shops that belong to the same chain in Lower Manhattan, in New York, in the US. So here we have essentially we have vertices and edges. And what we want to make sure is that if we have to choose locations of shops from this array, basically we would like to, the goal is to cover the largest area in Lower Manhattan, but basically under the constraint that when we consider placing shops between vertices that are connected by an edge, we would like that we don't want two shops on those two vertices, because otherwise they would compete for the same customers, essentially, because they are sufficiently close. So now, given this example, which is, again, inspired by a classical or a real-life use case, the question we want to ask is, okay, but how does our quantum computer help with the solution of this classical problem? Well, one way to enable the solution of this problem is by first reproducing the same network with our neutral atoms. Of course, we cannot place these two atoms kilometers apart. We have to make sure that we scale down the network that you see here, or the array, down to micrometer scales, but still preserving the connectivity of the network, because we want to make sure that if two edges, if two vertices are connected by an edge, the same type of constraint or the same type of connectivity is preserved here. And the way to enable this type of constraint or feature is given by the mechanism of Rydberg blockade that I was commenting before. Now that we defined the encoding, again, we want to run quantum dynamics, similarly to what I was explaining in the case of the quantum machine learning application. Once we run the dynamics, we monitor the number of excitations, potentially do some classical post-processing, and eventually reproduce, scale up our network again back to the original size, and find the positions of the potential locations of our stores within the same chain. And what you see is that this particular configuration of red dots is an independent set, in the sense that it preserves this constraint that no two red vertices are connected by an edge, but also it is also a maximum independent set in the sense that you cannot find any other configuration with the largest number of red dots. Let me very briefly comment on the applications on the third category, which are quantum simulations. Here we could spend really hours on discussing about those, and that's why I don't want to do that here, but please feel free to reach out. I would be extremely happy in interacting with you about those, because I think that there is really a strong overlap with what you are currently investigating. And the first example that I just want to flash is on the creation of exotic phases of matter. In particular, there was a recent result in collaboration with the group of Michalukhin at Harvard, where the first example of a quantum spin liquid, which is again an exotic state of matter, predicted by the Nobel Prize winner Phil Anderson almost or even more than 50 years ago, in completely different context in physics, that now can be emulated or reproduced in the context of neutral atom Rydberg arrays. The second example is the simulation, again, of other correlated or quantum phases of matter, and in particular, their adiabatic preparation, which means, again, a slow variation of the parameters of the Hamiltonian in such a way that we can connect the ground states associated to two different, in general, non-commuting Hamiltonians. And what I'm showing here are just three different examples of a very well-known checkerboard phase, a start phase or a striated phase here, this intermediate. Let me briefly comment finally on potential or coming developments or future implementation or features of our machines. The first thing is that neutral atoms are extremely prone or available to scaling. In particular, there are still preliminary examples of the realization of thousands of traps. These were realized by a group at the University of Chicago. This is particularly promising in the context of devising or realizing a very large-scale quantum computers, especially because differently from other platforms such as superconducting qubits or ion traps, you don't need interconnections between small hardware pieces that will contain a smaller number of qubits. You could say, okay, 10,000 qubits still is not really equal to infinity, but it's certainly much larger than any device that has been produced up to now. The second feature is the second capability is called qubit shuttling, which is the possibility of basically moving the atoms around the field of view on timescales that are compatible with the preservation of coherence throughout the whole system. Again, the only way to be able to make sure that we are still fully coherent is to encode the degrees of freedom, the spin degrees of freedom, or the qubit degrees of freedom into hyperfine states. What are the advantages of qubit shuttling? Well, first of all, from the architectural point of view, we can design our quantum computer by basically defining what we would call a memory zone and the processing zone, very much like in our classical laptops, for example. The second thing, which is also extremely important, which is more targeted to applications in quantum error correction, is then noise resilience by applying or encoding certain types of quantum error correcting codes, such as the toric code that will require all-to-all connectivity, or, for example, the surface code. And there are, of course, there is this very nice recent paper that was basically about the enabling of this qubit shuttling, as well as this recent result by the group of Mishalukin, where they were able to show very high fidelity 2-qubit gates. So this is the roadmap of the development of our hardware. Today we are here. We have a 256 qubit machine that work in the analog mode with this field programmable qubit array technology. We are now focusing on this step 2, where we will enable the first creation of digital quantum gates. And finally, of course, in the near future, we would like to reach the step 3 with the fast scaling to noise resilience or fault tolerance. There are multiple ways. This is more a sort of business slide that might apply to some of you, perhaps, but not necessarily, to work with QuEra, first by basically partnering with us to solve some specific use cases that can be, again, inspired either by academic motivations or business use cases, business problems. The second way is to make sure to exploit our so-called premium access, which means combining both machine time as well as training and consulting. And finally, you can equip yourself or your institute with a nice QuEra machine by either leasing or buying one of our hardware. Let me, again, thank you for your attention. Please feel free to reach out to us. I would like to finally advertise an interesting event that I will be organizing. I'm the main organizer at KITP, at the Kavli Institute for Theoretical Physics in Santa Barbara, California, at the end of this year. Again, if any of you is interested in potential applications within the space, especially of quantum simulation, again, feel free to reach out to me at my email. And as you can see, the list of speakers is really amazing. So thank you so much for your attention, and I'm open also for questions or discussion. Thank you so much.
All right. Thank you for the great talk. If you have any questions.
You can simulate physical model
for example, carbon lattice, so that you can realize atomic scale, the quantum spin repeat state. So, okay, so after that, what's the next step? What kind of useful information can be extracted from your system?
Right. So you can see quantum simulation in different ways. What I presented here is the current implementation of neutral atom technologies, which falls within the realm of analog quantum simulation. In that sense, you are sort of realizing non-universal types of computation, in the sense that you are restricted by the dynamics given by a certain Hamiltonian. So suppose that you would like to be more ambitious and try to solve a quantum chemistry problem, for example, where you need to encode the fermionic degrees of freedom into our spins, basically, or spin 1/2 systems. Then what you could do there is to employ a slightly different technique, which is instead universal, which is the digital gate-based approach, which is what other platforms are currently pursuing, but still with sort of limited impact, in the sense that you are not noise resilience, and you do not scale your system up to the sizes that I've shown you in this presentation. So currently you are sort of limited, and the applications, but still the applications are very impactful, in the sense that realizing a spin liquid is something which is really challenging, has been challenging for the past 50 years. If you really want to solve other types of problems, you need to perhaps change your perspective and the encoding of your degrees of freedom into a different type of setup, which is the digital gate-based, or in the context of AMO, hyperfine states. Again, applications can range either in the space of quantum chemistry, for example, but if we speak about optimization, we can talk about I don't know, use cases that are inspired by finance, by logistics, by pharma. Pharma, again, is another example where you will need perhaps very heavy quantum chemistry calculations.
Show in your items.
Yeah.
So is there difficulties in doing that, or like?
So you mean from the experimental perspective or from the theory perspective?
Technical and experimental perspective.
Technical, I think I cannot really comment too much, because I think we have here our expert, Min Ho, if you want to say a couple of words. But I mean, what I can say is that the challenge there is that you cannot move, so very superficial, you cannot move the atoms too fast. In particular, the criterion is an upper bound on the acceleration. In principle, if you move the tweezer that hold the atoms inside at constant velocity, nothing will happen, of course. This is Galilean relativity. But again, if you accelerate the atoms, we have a certain bound. And in the study, in the paper that I was referencing to, they basically define what is the characteristic or the maximum value of the acceleration to be able to preserve coherence. So for example, the example is the following. So suppose that you create a Bell state when the atoms are sufficiently close by, then you move them around, and then you make them going back again to the same initial configuration. And then you study whether the state that you create or that you find after basically this whole path, this shuttling, is essentially the same as the one that you prepared initially. So the criterion, I would say, is more that from the technical perspective. I think, yeah.
What is your plan for achieving single atom state?
That's a very good question. So one thing that, of course, I didn't have time to comment is the fact that the architecture, from the architectural point of view, the fact that we are using, we can employ qubit shuttling to enable memory zones and processing areas is actually very similar to the model of computation, of digital computation, that I was explaining at the very beginning, in the sense that by having a processing region, you can apply simultaneously multiple gates at the same time on different types of, on different sets of qubits. On top of that, there are protocols to realize gates which only require global addressability. So already that is enough. There are protocols, we can talk about that. If you ask me whether a single qubit addressability would be important, I would say certainly it's an additional feature, but it's not crucial for this type of architecture. You can have photonic interfaces. You can have photonic arrays, for example. Yeah, they do single qubit addressability. So we are aware of that. We are also working on that. But what I'm saying is that from the architectural point of view, it's not strictly necessary. Yeah.
Nowadays, and as you showed, there is collaboration of quantum and classical law in computer. And do you think that if we make very large scale and high fidelity quantum computer, then we don't need any classical help? Or what's QuEra selection, whether it was quantum classically or totally quantum?
Oh, beautiful question. Beautiful question. Thank you so much for asking this question. Yes, so I don't believe that we will ever throw our classical computer or trash our classical computers. There will be always a classical component that will support our quantum computation. This idea is also, my perspective is also supported by the fact that what we are currently targeting are specific applications of quantum computing, in the sense that I was just focusing on 3 different classes of problems. But of course, the things that you could do with a classical laptop is what I would call a general purpose computer. So a general purpose computer goes much beyond the technicalities or the applications that I was talking in my presentation. I think that a potential good way to see the field of quantum computing at the current stage is that we would like to make sure that for certain types of applications, we can certainly boost the performance of certain algorithms. That's one thing. The other important thing is that a complementary view to answer your question is that right now there is a lot of interest, for example, by supercomputing centers or HPC, high performance computing centers, to basically make sure that they could acquire the technology of these new quantum technologies as a node for their clusters. So, and the goal there would be to be able to run what I would call the hybrid classical quantum algorithms. Let's take as an example, we can consider their quantum reservoir computing that I was mentioning. So there is clearly a quantum component to that, but there is also a classical linear regression at the very end. It's super simple. You can perhaps use your laptop, but we can imagine that by scaling the quantum system up and therefore having a lot of parameters, even in the classical case, to optimize, we might need a cluster. So that's a typical case where you want to do hybrid classical quantum. There are other cases which are inspired by quantum chemistry, for example, where we have algorithms such as VQE, variational quantum eigensolver, where there is a classical part and there is a quantum part. So again, we combine the 2 things all together. So I don't know if I answered the question.
Last questions? Yeah.
Please.
What is the difference between the analog and digital computation? So what I understand was the state and the operation of the operable or the name, but is it the difference comes in from the dynamic? And what are the advantages and the physical difference from there? And the second question is about I am actually very interested in quantum matter as well. So can you tell me a little bit more about how is it can be applicable to the equilibrium?
Right. Well, great questions. So first about the nomenclature. So the name dual mode. The dual mode refers to the fact that we have both an analog mode, which is a continuous time evolution of an initially prepared state. So the key word here is continuous time evolution. The second mode, which is the digital mode, refers to the fact that we apply sequential layers of gates, which represent essentially discrete quantum dynamics, again, on top of the same register. From the fundamental point of view, the implementations of the two modes can be done by encoding the qubit states in the analog case, in the ground and Rydberg, in the digital case, in the hyperfine states of the rubidium atom, for example. So there are also some fundamental differences. Regarding your second question about the study of equilibrium dynamics, the answer is, of course, you can. And there are two examples that I was showing, which are the creation of correlated states like or non-trivial states of matter such as the spin liquid, as well as, for example, checkerboard phases in the square lattice. But you can even be much more ambitious. You can, for example, say, look, I want to study equilibrium phase of matters or the ground states of my spin system in the array given by the map of the world, for example. It's a fair question in the sense that this is a question that might not be a textbook example, but still perhaps interesting for certain applications. Instead of having the map of the world, you could have the map of the Jong, you can have the map of Seoul, you can have the map of, so again, studying physical inspired problems on some classical inspired use cases or geometries.
All right. Thank you again for today, and thank you again for Tom to join us for the seminar.
Thank you so much.